looking at work and energy, and I need to give you the physics definition of work. Too often kids, when they think work, they think, oh, tiredness. I'm doing work, I'm getting tired. And tiredness is not the same as work. Expending energy and getting tired is not the same as work. In fact, tiredness is a function of power, which we'll talk about in a couple lessons. Work has a very, very specific physics definition. It says this. In physics, work has a specific meaning. If you're going to do work on an object, two things must happen. A force must act on the object, and the object must move through a distance in the direction of a force. Work is a scalar, which is going to be very, 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 very helpful, very, 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 very handy, very, 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 very nice. And it's calculated by force times distance. But F and D must be in the same direction. Force times distance. What are the units? Well, what do I measure force in? Newtons. What do I measure distance in? So it's a Newton meter, but you know what? We use it so often, we've given it a special unit all its own. J, which stands for joules, a scientist named after a scientist whose last name was Joule. Work is measured in joules, but it is a Newton meter for what it's worth. For you to be doing work, two things have to occur. A force has to be applied on an object, and that force has to be in the same direction, that distance that the object travels. Work is what times what? Force times distance. In the same direction. Work is what times what? Force times distance. Force times distance. Example 1. How much work does it take to lift a 12 kilogram mass from the ground to a height of 9.5 meters? You know what? This is about 12 kilograms. Right here. How much work does it take to lift this lead weight? 9.5 meters. What direction am I lifting it? What direction, what's the force that I'm doing work against? They are in the same direction. They're not perpendicular to each other. Oy. So, work, symbol W, equals force times distance. Which force did you say it was, Cade? You know what? That was mg, right? Times distance, although in physics we call a vertical distance a height. What would be a good letter to use for a height? (12) times 9.8 times 9.5. How many joules of work would it take? I'll go 1,120. I'll go to 3 sig figs. Is that right? 1120? Yeah. Joules. So I told you that lead weight is about 12 kilos, give or take a little bit. 9.5 meters. How high is that? How high is one story, roughly? Meters, please. About 3 meters. This is about 3 stories. This will be carrying this about 3 flights of stairs. Would that be tiring? You could all do it. Would you like to do it 10 or 15 times in a row? So you know what? 1,000 joules of work, not that much, very doable, but you'd notice it. I'm trying to give you what an idea of a really big and a really small number is. All of you can easily do 1,000 joules of work. Cross out the word Dominic. Oh, by the way, and you'll notice no direction. Justin pushes against a brick wall as hard as he can for 12 seconds. The wall does not move. Justin, have you done any work? No, why not? No distance. Now, I'm fibbing a bit, and in a couple of days, I'll tell you why, even though no work is being done on the wall, why you're actually getting tired, because there is an explanation that does involve work, but I got to get more complicated. Pushing a box along a floor requires a steady force of 22.5 newtons. If you push it for 13.6 meters, how much work have you done? Imagine the situation. You're pushing a box along the floor, so the force would be that way. Is the direction of movement also that way? The distance is that way. Is work being done? Yes. $306 joules of work. Now, what we're going to talk about in a couple of days is work also means something else. When you're doing work on an object, you're actually transferring energy. Here's what we would say. If you were doing this work, your body would have lost 306 joules of energy. The box would have gained 306 joules of energy. You good?
Yes.
Oh, okay.
Just want to grab one of the scales.
Okay.
Your scale, right?
Okay. 306 joules of energy lost by your body, 306 joules of energy gained by the box. Dylan pedals his bike up a 19-meter high hill. The combined mass of the bike and the rider is 65 kilograms. The bike requires a steady force to continue up the hill. If the hill is at a 12-degree angle, how much work does Dylan do? Ugh. Well, let's fill in what we got, little picture. What's the angle of the hill? How high is the hill? I could probably use trig, SOHCAHTOA, and things to find, don't write this down, this distance here. I don't need it. When you go up a hill, which force are you doing work against? Think about it. Gravity. What direction is gravity? Straight down. Did they give me a straight down vertical distance in the question? It turns out I can go like this, Kyle. Work equals force times distance. Which force? Fg. Work equals mg times the height. The amount of work to get up the hill is going to be 65 times 9.8 times the height. How many joules of work to get up the hill? 12,100? Jordan's getting his calculator. Excellent. Put your pencils down, look up. What if instead of 12 degrees, what if the hill was that steep? How many joules of work would it take? 12,100. What if the hill was that steep? How many joules of work would it take? 12,100. Now you all bike, or you have in the past. Which one of these would you be able to do faster? This one. Which one of these would tire you out more? The nice gentle slope or the really steep hill? The steep one. So you ready? I said work is not tiredness. Work is not tiredness. Tiredness is how fast you do the work. And we're going to give that a name. We're going to call it power. If you're getting tired, it's not because you're doing work, it's because you're doing work quickly. It's the difference between walking up a gentle slope, taking several hours, and climbing the mountain straight up. You'll get there faster. You're going to be tireder, more tired, because you're doing the work quicker. Okay? Is that all right? The back stairwell behind the field there is a very shallow stairwell. They could have made it steeper. I'm willing to bet the seniors and people that live down there couldn't do that. They can't generate that much power. They can't do the work that fast. You guys could. You're still young, most of you. Pick your pencils up. This is one of the nice characteristics about work. It's a scalar. In fact, put your pencils down again once you've underlined that. If the hill had done this, all work cares about is where you started and where you ended. Do you know how much work it would take to do that hill? 12,100 joules. Which means work is going to be the first thing that we can use to analyze yucky, curvy paths, like roller coasters, which are curvy loops. We'll look at amusement park rides later on this unit. Pick your pencils up. I should have said work, force times distance. The force has to be constant. What if the force is not constant? Like your balloons, which start out emitting a big force when the balloons were inflated, but by the end you weren't getting much from it. What then? Well, turns out there's another way to calculate work. It's also the area under a force versus displacement graph. I like this question, I like this question, I like this question. How much work was done in moving this object from 2 meters to 5 meters? Well, do you notice, Spencer, what was the force in newtons at the beginning? 2. What was the force in newtons at the end? Is this a constant force? Changing, right? It's changing. So I can't go 8 times 5. The answer ain't going to be 40. Is there a graph? A force versus displacement graph? It turns out the work is going to be that area. For a candy, who can tell me what we call that shape there? Really? It's not a square. It's not a triangle. It doesn't begin with a T. Carson, sorry?
Trapezoid.
It's a trapezoid. You get a candy. Now, for 2 candies, and only once have I had a kid pull this out of their hat, who knows the formula for the area of a trapezoid? There is one. Do you know why we don't teach it? It's redundant. It's redundant. It's unnecessary. Because any trapezoid that you give me I can do this and turn it into which two smaller shapes? What's the bottom shape? Which we have a formula for area for. What's the top shape? Which we have a formula for area for. But there is, for what it's worth, nerdlings, an actual formula for the area of a trapezoid. Anyways, candy for you later. Make sure I'll give it to you at the test, maybe. Remind me. Okay? I'm going to call this area 1. I'll call this area 2. The total amount of work is going to be area 1 and area 2. Why? Because it's a force versus distance or displacement graph. Anybody remember what the area of a triangle equation is? I might have put it on the formula sheet. I don't think I did, though. Base times height divided by 2. Divided by what? 2. Divided by what? 2. Why does that work? Don't write this down, but you can watch. Because, Kyle, any triangle is half a rectangle. It's really length times width divided in 2. Take the length, take the width, but because it's a triangle, we'll call it a height divided by 2. Okay, smarty peoples. How long is the base of the triangle? 3? Right, from here to here. What's the height of the triangle? Goes to 8, starts at 2, 6. Divided by 2. And somebody already called out the answer. It's 3 times 6, which is 18 divided by 2. What's the area of that top thing? 9. Area 2 is a rectangle. I hope you all know the equation for the area of a rectangle. How do I find the area of a rectangle? Natalia. LW. Natalia, what's the length of that rectangle? 3. What's the width of that rectangle? What's the area of that rectangle? How much work was done in moving this object from 2 meters to 5 meters? 15 joules of work. Madison, when it asks how much work, you're first of all going to say, is it a constant force or not? If it's a constant force, see, there's 2 ways to define work. Work is force times distance. It's also the area under a force versus distance graph. Do you know how you're going to know to use the second one? Because there's going to be a graph in the question. Sorry, Captain Obvious, but oh, he gave me a graph. I bet you the force is slanty, not constant. There is a third definition of work that we'll talk about later. Okay. How much work was done moving this unknown object 10 meters? Well, it's going to be that area. Carson, what shape is that? Trapezoid. The trapezoid. Do I have the area? Oh, wait a minute. Any trapezoid can be broken down into a triangle and a rectangle. It's going to be area 1, area 2. You guys can try this on your own. I won't freeze the screen. I'll just write up here. See if you can get the area of the triangle, this times height divided by 2, the area of the rectangle, length times width, add them up. See if you get what I got. I think you can do most of the math in your head because it's your 10 times table each time, yeah? I got 100 divided by 250. You got 10 times 20, 200. 200 plus 50, 250 joules. Let's put it all together with the stuff from last unit. Okay. A 124 kilogram mass is being pushed along the floor that has a coefficient of friction of 0.25. Person pushing applies the force 525 newtons over a distance of 22 meters. We're going to do a free body diagram for this, trust me. What are the forces acting on this here mass? The obvious one.
Gravity.
Yep. Is this block sinking into the ground like quicksand? Is it flying into the air like Superman? There's an applied force. And they even told me how big the applied force is. So I'll stick it on here. 525 newtons. And it does talk about friction. Gotcha. And can you read to me A?
How much work is being done by the person pushing?
Which of those forces is the person pushing? In my free body diagram, which of those represents the person pushing? Okay. This is really saying find the work done by the applied force, which is going to be F applied times distance. Did they give me F applied? Did they give me the distance? How much work was done by this person? 525 times 22, 11,550 joules. Is that okay so far? Oscar, can you read to me part B?
How much work is done by friction?
Well, I guess the work done by friction is going to be the force of friction times distance. If the work done by the applied force was the applied force times distance. You okay with that? Hey, friction is what times what? This is going to be mu times the normal force times distance. I don't know the normal force. Oh, but look. I know another force the same size as the normal force. Which force is the same size as the normal force? So if I hear you correctly, Kyle, you're saying it's going to be that. I'm going to get the work done by friction is, what's mu? I don't know. What's mu with you? 0.25 times mass. Did they give me the mass? 124 times 9.8 times 22. How much work did friction do? You get 6,683.6. Except I'm going to be a little fussy here. What direction is the box sliding? To the? What direction is friction? They are in the same plane. How could I show that the direction is opposite of motion? That's not a vector. I'm not actually adding a direction. It turns out what I'm really saying here, Colin, is that's lost energy. And how could I represent the word lost mathematically? With a negative. This person is pouring in 11,550 joules of work, but not all of it is going into the box. Some of it is going into, to be honest, heating up the floor with friction. Some of the energy is going off into heat. How much? 6,683.6. In fact, part C says, what's the net work done? How much in? Now, I can do this two ways. I can either go take away 6,683.6, or I can go plus negative 6,000, but I don't want to go minus minus. That's all I'm saying. What's left over? The net work that's being done is 4,866 joules. 4,870, I'll go to 3 sig figs now, joules. Okay. Work. That's your homework. Work. Number 1. Number 2. Number 3. Number 4. 5 is good. 6 is good. So far I'm assigning everything, but you have lots of time. 7 is good. 7 is a little more similar to what we've just been handling here, except the fact that it's a steady speed means your forces are balanced. You can figure out the applied force, I think. 8 is good. Hey, here's a force versus distance graph. And then I got a couple of videos to show you.